We are sending data. We are good. Good. Yeah, we're good. Go ahead. Bring this one online. Da-de-da. Okay, so we go to stream. I need to go to my events. Okay, we should be streaming to everyone. Let's see. Okay, looks like it's good. I'm gonna look forward real quick, see if this lines up. Okay, so we seem to be good. We got about a few people, a few on Twitch, a few on YouTube, a few on LinkedIn. Okay, so welcome to the stream. I'm FPGA Zealot. We'll be starting in like 4 to 5 minutes, digging more into details, but feel free to say hi in the chat. Talk about how you came here, FPGAs, AI, ask any question. We can have a little bit of a conversation before we dig into the stream. It make sure audio's good, make sure video's good, but yeah, feel free to say something in the chat. I'll try to keep up. Okay. So this stream, I'll probably repeat this a few times, but this stream is about getting streaming, working with the FPGA AI Suite little IP core. We're going to be using some basic Onnx models to configure the model within the core. Like what you see on screen, this is a basic Onnx model, and we're going to get data streaming in and data streaming out, and have working custom core where we can play around with the data input, the data output, and the model without much of a larger API or software suite to get everything running. This will allow us to do I guess validation of the streaming input and outputs, play around with some basic formatting for the input and output on the model to make sure it's right. I'll look at trying to put the model into the DDR, but that requires some DLA, the DLA compiler to get that binary set up, and I wanted this to be much more easy. Let's focus on one thing. So we're going to focus on the stream input, the stream output, the model. Then we can add the DDR, put in a larger model, and then try to get data actually streaming through this interface. This is sponsored by Altera. They provided the hardware. This is I guess a paid stream. But thank you for joining us. We're probably about around 10 people. Make sure chat is working. There we go. Okay. Once again, if you're joining us now, feel free to say hi in the chat. We'll begin in a few minutes. We're going to be looking at some basic configurations for Altera's FPGA AI Suite IP core, and implementing it on Agilex 5. This example would also really work really well on Agilex 3 and Agilex 7 and ARIA 10. I mean, maybe I should pull out my ARIA 10 board and get this working on the ARIA 10 board. This should be a relatively simple configuration to get running on anything. Agilex, ARIA, Stratix. So I would say ARIA 10, Stratix 10, and the Agilex boards. I haven't really seen Agilex 9 examples. I would love to, if we can get something working on like a Cyclone or a Max FPGA, but The internal local memory requirements for a system like this are too great for those smaller FPGAs for this, at least the current solution. But it's interesting. Okay. Ah, got a good amount of people there. Ah. Okay, it's I guess the top of the hour, so we can officially begin the content of this stream. So welcome to the stream. I'm FPGA Zealot. I like to do FPGA tutorial videos, I guess FPGA videos in general, and I want to focus more on the advanced topics. I want to focus on things that are cutting edge, something that's new on an FPGA, more advanced interfaces, stuff to help, I guess, companies, startups, hobbyists be able to get something more cutting edge, something that is competitive to current products on the market. I want to, I guess, help that education be more public and have people examples to dig through it. These live streams, I like doing live streams. I want people to walk through the tools, to be able to ask questions, to see someone develop live, to debug live, to be able to handle the tools. There may be crashes, there may be some issues that hopefully be resolved. For this stream, most of the stuff has been pre-compiled, pre-built, and tested, so there's not too much live development, just mostly because FPGAs take a long time to compile. But thank you. So today we'll be looking at the FPGA AI Suite on the Agilex 5. We'll be looking at the Onnx test models to help us do very basic models and just get data, validate the data input and data output for our model. That way we can play around with the, I guess, the FPGA interaction side before start working on more complex models. Let's see what else is to look at. So once again, I'm FPGA Zealot. You can find me on YouTube and X and Twitch, and LinkedIn. I'm Andrew Wilson. We're streaming on 3 of those. I might stream on X in the future or look some other options, but right now we're just doing YouTube, Twitch, and LinkedIn. Some basic disclaimers. This is a paid sponsored live stream. Altera provided the hardware. They provided some, people to contact, ask questions for. I am not employed by Altera. I am not their field application engineer. I do not provide professional support for products. Most of the content on this channel is great for information purposes only. I want people to have examples. Feel free to ask about the examples. You can ask additional questions in the chat or the Discord or whatever for what you're working on, and I might be able to talk about how my examples relate to what you're working on, and it's a good way to share what's happening in our, I guess, this little community. All the opinions expressed on this channel are my own. So today we're going to the Agilex 5. We'll probably walk through these slides relatively quickly. We're mostly focusing on what an FPGA is, what the Agilex 5 is from the Altera is. So we're looking at the Agilex 5, I believe, E series. This is I was it 7 nanometer processing node or 5 nanometer processing node. Well, it's a relatively modern, fast FPGA. Altera says for most designs you should be able to get up to 600 megahertz, which is like really a good benchmark to be able to get an FPGA design up to 600 megahertz. Normally I'm doing soft processors. With soft processors, there's a lot of interaction. You can't really get up to 600 megahertz. 250 megahertz is usually a good speed for a soft processor, even on these FPGAs. But if you're doing more, I would say, traditional FPGA design, doing processing pipelines and whatnot, being able to get 600 megahertz is a very good value. I would love to dig down more into doing some more complex designs in here, but that is something Altera talked about in their recent PR events. Other things about the Agilex 5, they have new DSP units. A DSP is a little integrated digital signal processing core that's in the FPGA fabric. They added a new functionality with the Agilex 5 family that allows it to do convolutions over like 10 coefficients and 2 kernels. So you can do a lot more convolutions within the fabric. Compared to competitors, this is about putting the accelerated convolution feature integrated in the fabric instead of having it as a separate solution on a different chiplet. Which I think you can do some really cool designs. I hope that we can see more IP, whether video, whether AI, or other things that take advantage, or radio processing as well, that take advantage of these integrated DSPs. So we'll be using the modular dev kit. I've liked this modular dev kit. The display port works great. The PCI works great. I haven't really played around with the FMC yet. The HDMI, I need to look at the new revision. I think they did a revision to fix some of the issues with the HDMI, but I think this is a really good product for the price point, last I checked, that offers basically all the advanced interfaces you would want to work with on an FPGA. There is a processor, a system on chip, that provides, the 2 ARM processors. Let's go back to the previous slide. Dual core A55, dual core A76. So you have 2 real-time, 2 application processors. I haven't done a video recently about building that image for that, but Altera has posted some new tutorials and guides to build the Yocto image for that. There are no bare metal examples at the moment for those processors, mostly Linux examples. Okay, so today we're going to dig down into looking at the FPGA AI IP core. How do we use a DDR3 architecture with streaming inputs and streaming outputs? How do we develop the Onnx model that goes through it? And then after that, we'll look at adding that IP core to your existing design and then verifying that with signal tap. So let's see, let me pull up, we can go to the flow real quick. There are a few steps to getting AI working on FPGAs. This is gonna go. There are a few different steps. First, you need to configure your FPGA, configure the software interacting with your AI core, configure the data interfaces for your AI core, get the model working, get that all. There's several different steps. And we're looking at generating the architecture first. So we're looking at mostly this step, compile. And we are creating an architecture. And I just want to see where the architectures. That's okay. We're generating an optimized architecture. Is there another thing for doing an architecture? Yeah, let's see. Okay, so we go here. Where do we talk about the architecture? We'll look at DDR3 operation. Utility. Okay. So there's a lot of different architecture optimizations. Well, that's not really what I'm looking on the parameters. Where? Here? Okay, yeah, right here. Architecture description file. So we have a lot of different ways we can configure our architecture. That's what I want to focus on. And we have that fun little picture somewhere. I have too many tabs open. Okay, here's the picture I want to focus on. So the architecture is going to define what's in our IP core. And the IP core has various different stages with, you know, FIFO, scratch pad size, different, you know, convolutional sizes, activation pool sizes. And the architecture file, it works on this, or defines what we're doing here. And you can optimize it based on the FPGA or space you want to look at. We're also looking at DDR3 operation, so that we don't have to rely on the DDR configuration for operation. So let's jump into the architecture real quick. So this is the Agilex 5 architecture. There's like an Agilex 7 example, but here's an Agilex 5 example I was able to get working. I should probably find some time to break this down into some more detail, probably in a written guide rather than into a video. But we want to look at this architecture that's going to define the AI core that Altera is going to provide. We had a question from YouTube. What's going on here? So we are configuring the FPGA AI core for Altera FPGAs. This architecture file defines what features and settings are within that IP core. It'd be really useful if this was a GUI, but right now they're at the stage where it's more of a like an XML file. Well, not XML file, but like a description file of some type, which you define what features you're looking at, what sizes, what interconnections that you need to have to get your AI core working. So here's an architecture, and I want to use this architecture to build a model. A model, if you looked at previous videos, we have an Onnx file. That Onnx file is converted to an XML binary file that we then can like configure for the architecture appropriately and get a binary that we then can like execute on the system. So what we're going to do here, and delete these two. Yeah, delete that. So I have a Python notebook page that's going to generate a very basic Onnx model. So what we want to do here is we want to do like a pass-through. I did have a large language model help me with this code, so the comments and whatnot that's from having a large language model kind of guide me through how to get this really basic Onnx model up and going. But basically, we're going to have a single channel, 32 by 32 floating point values as kind of like a pseudo image. We're going to define those as the input and output. We're going to create a weight matrix for our convolution. It's going to be the same shape as the input and the output. And the very middle, we're going to make a 1. So we're going to make an identity matrix that we're going to put into our convolution. And then right here is where we define our convolution. We're going to take our input, our weight matrix, and our output, and just create a very basic convolution. And then print that as save that as an Onnx model. So we can just run this. And so we now have an Onnx model over here. We can't view it in the tool, per se. There might be extensions, but we can also use this tool. So this is the Onnx model we just generated. This Onnx model is kind of industry standard across all the different AI tools. So that's really useful that we can use this standard format, and we can, you know, run this locally on any tool, or we can run this on our FPGA AI IP core for hardware acceleration. And we can, does it define the input very well? Okay, so I mean, like we have flow 32, we have the shape, we have the convolution here. The kernel shape is 3 by 3. We click this right here, we can go into the weights. We can see that the middle is a 1. So that is our convolution, and then we output that convolution, the shape of 1. So I think we're just outputting that single value, and then we're just mapping it back to the 32 by 32. And this is float 32, and that's our output. So next, we can use the model optimizer that's part of the DLA toolset, and we can convert that into a binary. So now we have an XML file that, has a pretty good description of the system. We can see, does it describe the weight matrix? I don't really see the weight matrix here. It must be in the binary. And then we can, this is using the compiler tool, the DLA compiler tool. We can pick our architecture, we can pick our XML file, and we can output it. So what we're now is we're going to take that very basic Onnx model and make, where's the output? I feel like my output should be here. Let's try this again. Does the output come out? Why the output is showing at the moment. Okay. So then if we go to here, we go into this dot file right here. Back over here. This is our model as the DLA compiler sees it, right? So here's our constants. We have the one in the input in the middle. We're going to convert that to match, I guess, the shape that's coming in. We're going to have float 32. This is the FPGA input. And then we have our convolution. And then we have our output. I don't really have the shape right there. There's other visualizations. Let me see if anything else is useful. Okay. So those are our various dot matrices. Now we're going to use the DLA create IP core to create the IP core that follows these configurations. And part of doing the compiler, we created these parameter ROMs. And is there any like non-zero parameter ROM we can look at? So we then load those parameter ROMs into the IP core when we generate it. So we've created the Onnx model, a very basic model. We optimized it with the DLA tool set. We compiled it for the architecture, and we have built the architecture as an IP core for the FPGA. Okay. We can now look at it in the tools. Okay, we just got a question from LinkedIn. Will their session be recorded? This should be recorded on LinkedIn, Twitch, and YouTube. So whoever one has the best recording, you should be able to rewatch these anytime on any of the streaming services I'm using. So feel free to rewatch these sections, to go through it. There's a link for my Discord if you have questions about the examples or need source files or something like that. I can help walk you through those things. So next we're going to go into our Cordis tools here. Let me kill this. So I just want to show you how you bring in this IP core. We should probably take a moment. Okay, so we're going on to the next step here. Go here. So we're moving on to the next step here. We're going to look at how we build the AI core, add it, and look at the settings. If you're just joining us, I'm FPGA Zealot. We're doing a Altera sponsored stream on the Agilex 5. We are looking at using very basic Onnx models and to do data input streaming and data output streaming. This is sponsored by Altera. They provided the hardware and some expertise. But hopefully we can. If you have any questions, feel free to say hi in the chat, add your question, and we can move forward. So now we're going back to the tools. We're going to create a new project, and we're just going to target the dev board. So we're just going to stream IP example test project. Okay. So we're going to use a predefined hardware. That's the modular kit. We're going to use the first revision right here. So this is the Agilex 5 E series, right? No, that's not right. Yeah, it is the E series. So next, we're not going to add any files at the moment. We're not going to worry about the simulation at the moment. We're just going to add the IP core. So to add the IP core, we're going to right click into files. We're going to add or remove files in our project. We're going to go to the IP section here. We're going to do project specific. And we're just going to go up to that folder right here. We created this temp IP directory. We're going to choose this. We hit OK. When you go a folder down. Yeah, oh no, did I not add it correctly? Sorry. I have to hit add afterwards. Choose, add, apply, OK. Now we have an FPGA AI Suite in our library. We double click this. Yeah, create the AI IP core. So this is the IP core we created with the DLA tools. If we have multiple architectures, we can put in the different architectures here and be able to switch through them. There are DDR parameters and there are streaming parameters, but the streaming parameters are locked down. They can only be used through our little architecture file. For the DDR parameters, I think you're set. I don't think you can change these if you want, but I don't think there's any need to. So we're going to go ahead and generate it. I just want to show you what happens if you attempt to generate some simulation files. Just mostly because simulation is not currently supported with the IP core. And you'll get an error. So I just want to show, if you go through and you try to generate simulation files, that's currently not supported for this IP core. I'll try to get some updates on the simulation status for this later. But for now, we want to do no simulation, and we're just going to generate the Verilog. And we can close this. We can close this. And we now have an AI IP core right here. I didn't want to reopen it. And then we can go look at the instantiation template. Okay. Okay, so if we go back to our VS Code, we're going to go into that folder. So we did stream IP example, AI IP. Instantiation. Okay, here's our instantiation. You have control status register bus, your DDR bus, and your streaming bus. And then you're going to hook that up to your system. You can also use the block or the system compiler, the system tool, also the visual block diagram. I guess we could try that real quick. I'm curious how that works. So we go to tools, we're going to go to the Visual Designer Studio, and we're going to create a new system. Yeah, sure. I just want to add the IP core to here and see what happens. I haven't done this yet, so this is we're improving here. So get this in the middle screen, make this big, I guess. We're going to add, no, that's not what I want. Add IP, AI, FPGA AI Suite, right here. This is the one we compiled, right? The streaming architecture. I'll hit finish. Okay, so this is the block designer. And then we could add the control status axis, the streaming inputs, and the DDR interface. I'll have to maybe look at doing this later as we get better at using this tool, but this is a way we can insert it into our block, our Visual Designer Studio. Okay, so we're not going to worry about this. We're going to go to my pre-done design where I modified the JTAG system, and we can go through that one. So if you watched the previous video, I talked about how we can update the HDL files, how we add the actually stream inputs between the system and the AI core. The only difference I've done here, I've added some fixed values to make the demonstration of the data a lot easier. And we have fixed the valid for the inputs high so that the AI core will constantly congest data. We've done a fixed value. This is dummy data. It's not fitting the float 16 or 32 that we're expecting. And then we have the output ready at constantly high so that the data constantly comes in and data constantly comes out, and we can see what it looks like for latency and clock cycles. So we're going to look at how the streaming input actually operates, and see what data values come out. I know that doing float 32s with invalid values may get a little weird, so I may need to look in how to do some valid values through there and to figure out what the input and the output should look like. There's a lot of documentation that we talked about last time about different folding options for the input and the output and how the data is arranged. And I think I need to go learn that format better so that I can demonstrate for you guys here. So we've gone through the whole system of compiling this new streaming input and streaming output. We're doing, even though we have a connection to DDR, we're doing a DDR-free implementation because we have added the parameter ROMs to our IP core. So the model is baked into the local memory on the FPGA. Okay. Take a quick breather. If there's any other questions, feel free to ask. We're going to be moving on to the next state where we're going to be actually verifying the input and the output of the streaming interface using the signal tap. Let me see if there's anything on here worth talking about. So yeah, there's an Agilex 7 option, and that is right here. If you want to look at the Agilex 7 example, you can do it from scratch. Do they have like a little picture of how it's working? Architecture. Yeah, we want to do something like this to figure out the best way to do some data. Oh, are they using local VRAMs? Yeah, it might be better to do some local memory. Is there anything else useful here? System console, measuring performance, updating MIF files. This is what I want to look at. So you don't want to potentially rewrite your entire FPGA or recompile your entire FPGA when you have a new model. So right here we have really useful tool. So you're going to recompile the MIF tool or the memory instantiation files using this, then replace in the directory, and run the following commands from hardware. And that should update the contents of the M20Ks. That's useful. Okay. Updating the memories. Any other questions? Okay, we're going to go on to the next step soon. Let me pull up. Yes. Okay. So for the next step, we're gonna spend the next last session looking at the streaming inputs and the streaming outputs for the system. So we're going to use signal tap and be able to monitor what's happening on the data. It's going to be this one right here. Where's that picture that we were looking at? Right here. So we're going to monitor the Axe4 streaming input and the Axe4 streaming output to see how the data is ingested and how the data is processed on the egress, the output side. So to do this, we're going to set up signal tap. So we're going to signal tap here, and we're just going to grab the basic AxiStream interfaces. I really like AxiStream. The protocol is very basic and it's useful. But for the input stream, we have T-data, T-valid, and T-ready. There's no T-last. There's no T-strobe. You're expecting all the data to be available at the same time. I don't know if there's other options that we can enable that within the settings. We can take a peek real quick at the documentation if we can change that real quick. If we look at input streaming, yeah, just T-valid, T-ready, T-data. There's no T-strobe. There's no T-last. Right, there's nothing input true false, FIFO depth. Yep, that's all you're really doing. And then for the output, we have ready, we have the data, we have last, strobe, and valid. So the last is just showing you when the full model has been completed, and the strobe is showing you what bytes are enabled on that AXI stream. So you may not use all the available bytes, and you may be using a subset of the full system. So once we've got this up and running, we can go ahead and let's reconfigure this real quick. Yeah, I should be able to reconfigure it. We're going to reprogram this, and then we can look at some stuff. Let's make sure this is not running. Okay, it's not running. Okay, so we have this configured. Let's go ahead and just look at the data. That's the old data. Let's look at some new data. So at rest, we have our fake data here of dead beef, cafe taco numbers. The valid is high on the input stream. The ready is high on the output stream. So the system is ready to run. We still need to use the control status registers, the CSR registers, the CSRs, to be able to get the system up and running. So to do that, we're going to interface over a system console. If you've seen this before in my previous streams, we have a little tickle server that connects it to Python, and we can interact with the hardware in the Python notebook. So right now we're going to enable the tickle server with the system console. Then we're going to jump into our VS Code, and now we're going to scroll down to, hopefully the output's coming. Okay, why are our outputs not showing here? Okay, let's open that up again. I want the outputs. There we go. We have the outputs up here. Okay, the outputs finally show. Okay, the kernel is still running. Let's see. Okay, the kernel is still running. So we're going to, that's just a dummy read. We're going to reset the system. Oh, I should show you these registers real quick. So these are the DMA control registers. We are resetting the IP, and now we're going to activate streaming. And I assume this is just going to immediately use the DDR-free model and the streaming input and the streaming output. We just have to turn that on. So that's going to be this right here. But let's go ahead and get the signal tap up and running. Signal tap right here. So we're going to trigger on the output going valid. And this will happen kind of like in the middle. So we should be able to see everything that's going on. We have the acquisition in progress. Now we're going to go back to our Python notebook page, and we're going to run the start. This black-white bit rate. Not going to be happy. So here is the data operating. The dummy data is not floating point, so the outputs are a little bit confusing, but I hope I can get some better examples up and running soon. But we can see this is the ready going up and down. We're reading, what's this? This is like reading one. Where's an easier place to count? Right here. Let's go right where the trigger is. So we're reading 128 bits every like 16 cycles. And then we have the output about that rate, one every 16 cycles. And so you look at the very first 367, 445. Is that the very first one? It is. And then 0. Looks like it's starting at the lower bits and walking back up. Yeah. Cafe. That was taco. And this was cafe. So it's doing it's doing 16-bit. It's converting this into several 16-bit floating point values. So if this was like 16 bits floating point, I think we would actually see better results. We can see this configuration in the architecture file. So going back to the architecture file, our lightweight transform is taking 128 bits and converting it to float 16, which is then converting that to 32-bit floating point for the model, and then probably converting back to a different value on the output. So just kind of understand the data here. We can zoom out. This is when the model, I guess the AI core turns on, right? So this is going to be our first, right here is our first data packet. Let me see. Go here. So right here is our first data packet, like our first model input. Then here's our second model, a third model, fourth model, fifth model. So we're buffering multiple inputs together. And the data processing happens about halfway into our fourth. And then later when the buffer clears up, we can load in the new input. And then later, we can load in a new input. Right here, this is the TLAS signal going up. So from, I guess, the input, which is about negative 4,000, to when we get the data is 16,000. So there's probably about 20,000 clock cycles between the input and the output. But if we look at, we don't have enough data at the moment to see how well this is pipelined, but it looks like it's fully pipelined. So every 16,000 cycles, we should get a new full output. And this is kind of a pass-through model. So I'm not sure how other models will work. There might be better ways to pipeline these, how this works. It'd be interesting to try different model configurations, more complexity in the Onnx model to see how that affects latency. Maybe get a counter from when, like the ready goes high to when TLAST go highs, and we can just start collecting counters in the hardware, because it's we're not going to have enough of a long enough of a signal tab to see the whole transaction like this very basic model. So this is like this is a working example of getting the ActuStream input and the ActuStream output with the Onnx model. I think it's time we can probably take some questions in our last 5 minutes of the stream. What could we do? We could try to do 16-bit values. Yeah, let me try generate some 16-bit values. Maybe we can, it's gonna take forever to rebuild it. I'll just start rebuilding it and we can maybe post the results later. Okay, so I'll close this out. I want to modify this guy and then rebuild it. It's probably gonna take too long. It's gonna take 20 minutes to rebuild. Yeah. We can talk. But thank you for joining us on the stream. we'll probably do some more content later this week. I have a computer vision development product I would like to look at on Saturday, and then I'll look at some high-level synthesis next Tuesday, and we can talk about those examples. So what we need to do is we need to modify this. So I want to do 3800 3C. I want to build this 3C 0. Um, 1000 divided by 1. This is what 16-bit could look like. I guess we could just do the whole model and try to get this up and running. Okay, I'll do this step, then I'll increase other things, and we can see how that works. Okay. See what those values look like. Then I need to update the architecture, copy things over. I guess that'll work. Any other questions? Thank you for joining us again. How do we validate XDC, SDC constraints in this flow? Say we got a floating point, MCB wrong. How do you find it, please? So you want to evaluate. So you got the constraint file. Let's see. Let's make sure I understand what you mean by FP or MCP. But I mean, there's the results here. You can look at how the constraints define the model. And the reports, where are the reports? Just review reports, completion report. I just, wipe them out so we can't look at them right now. But we have a question on false paths and multi-cycle path. Okay, that's what you meant. So I'm not terribly good at doing multi-cycle paths. Every time I do it, it doesn't seem to work as I expect. Maybe figure out how to get those working the way the tools expect them to do. But the IP core should include some constraints. So let's look at the SDC file here, right? Verilog. So where do we have the header file? Resolve system Verilog. Okay, here we go. We have the cross crossing synchronization are defined as false paths right here. And we have header files. Anything else? Is that the only clock crossing that they worry about? Not seeing anything else pop up. But that is a lot of files. Okay. Yeah, that's the only STC file they have posted. I guess we could look at to see if there's anything inside this guy. Just the project header file. So it looks like that the false paths are defined by the AI core. IP generation. I didn't see any multi-cycle paths. So the old HLS tool is currently what's it? The Altera HLS tool is in transition right now. It's transitioning from Intel to Altera. And I believe the next Quartus release should have more information on how Altera is going to approach HLS in the future. That was something I tried to run the tools, and right now they're not currently the Intel HLS flow is not currently supported, but they're still transitioning from the Intel to Altera. A lot of the documentation is kind of split between Intel hosting and Altera hosting. Some of the tools are kind of split between Intel hosting and Altera hosting. And I think once they get their Altera hosting up and running, we should see the new iteration of the HLS tools posted. And I expect that will be probably early 2026 Quartus that we'll see the HLS tools and tutorials come back. Okay. Back here, I guess. That's going to take time. So I was hoping to learn how to get the streaming data working. I hope to get this working with real data. We have the DisplayPort example that we worked on 2 weeks ago, and we can use the DisplayPort data to as the input for the stream. Are there any good examples that you'd want to see from the model? It doesn't have to be DDR free, so I might be able to do a classification model. I need to figure out a good way to downsample the image. So if we have a 4K image, I need to downsample that to what, like 49 by 49 or something like that. So I need to figure out how to downsample the 4K image, provide that as an input, and then figure out how we can apply the output. It'd be cool if we could do box bounding, like real-time box bounding with like the label. But box bounding's a little complicated. I can definitely do a label. Segmentation, I think, would be really interesting. I may need to look at how the segmentation model output works, and we can do color segmentation on the picture, and that would be really, really interesting, like real-time image segmentation with a model. Any other suggestions for processing real-time display data through a model? We can do classification, try to do some box bounding, we can do segmentation, we can try to do license plate, identify a license plate and read a license plate. I think that'd be interesting. If we could take a picture of a road, do segmentation, classification on the road, get the cars. Once we get the cars, try to identify the license plate location, then downsample to just the license plate information, and then do license plate reading as a model. I think that would be a really, really fun way to just monitor the cars going through traffic. But it takes a lot more work than I probably can dedicate at this time, but that'd be a really fun project to demo at some point. If anyone has any questions, feel free to talk in the Discord or leave a comment. Here we walk through a custom architect file. The lightweight layout transform parameter is new. It's on the 25.3 tools, or the newest set of tools. I'm not sure how well that is with the documentation as we transfer from the Intel to the Altera hosting. I do want to do 32 on this. I do want to push this to 128. If I can reduce the buffering on that. I'd like to see how that looks. And then for our Onnx model, go back here. We did a very basic convolution. It might be interesting if we throw in an activation layer or a pooling layer or something like that afterwards and see how that affects the output. And we can play around with input size and output size for these basic Onnx models and get that working in hardware. And as long as we keep the basic architecture, we should be able to just update the MIF files and not the memory instantiation files without recompiling the whole system, which should be good to go through that debug and development flow, so it's easier to follow. And then we, using the DLA utilities, we are able to optimize that Onnx model to a kind of XML binary file. We can compile it against the architecture. And then once we have that, we can create an IP core with that architecture file and load in the parameter ROMs. And then we can load that into our FPGA design. It'd be really cool. We can get this working in the visual designer in the future. That'd probably be a great video. Just like, okay, let's just go from JTAG, the visual designer, go through the basic steps. I will look into doing that. That would probably be a great way. Like rapid prototyping with the FPGA AI core. I'll look at getting that working. That would probably be a more of a good article and a video combo for that. Maybe add PCIe as well. Do PCIe, JTAG, DDR, stream-free DDR architecture, maybe an IL or a signal tap core to monitor it. That would be a good like rapid development cycle. I will look into that and see what progress we can make. That would be really interesting for me. I also want to look at bringing in data over the FMC. I have a ADC and DAC, and we can do LVDS data and process LVDS data as well. So creating one design, PCIe, DDR, JTAG, DisplayPort, FMC, maybe an AxiSwitch SMUX. We can change the data and how we're processing it. Maybe a smart processor, maybe we can get the Yocto image working as well. That sounds like a fun project. I may look into that, but maybe later. Okay. Any other questions? So thanks for joining. We're probably going to, let's see how close this is to being ready. We're still like 10 minutes out. So I'm probably going to close the stream before this is done. Hopefully we can talk more about this in later videos, post our article or something like that. Feel free to leave comments, like, repost, subscribe, whatever you want to do to support this content if you want to see more of it. The Discord's already open if you want to talk about specific examples or FPGAs in general. But thank you for coming. I enjoy doing this. This is more of an opportunity for me to explore FPGAs and their advanced features and share with others in the community. Feel free to join us for the other streams. Probably one on Saturday, definitely one next Tuesday, where we'll talk more about different FPGAs and different FPGA applications. Let's go to my closing slide as we finish up. So this is FPGA Zealot. I'm going to say bye now, and we're going to say bye to each of the streaming services. We'll say bye to LinkedIn first. Say bye to YouTube. And we'll turn off